welcome back, and today we're going to write some assembly for this big blue beast behind me. This is my Centurion mini computer, and it is a mainstay of the channel. I've actually been going a little hard on the Centurion episodes recently, but that's because I'm trying to build up a second Centurion with a working hawk drive in it to take with me to New Jersey where VCF East is happening. But the key word there was a working hawk drive. I only really have one working hawk drive, and I'm not insane enough to take my only working drive with me to New Jersey. So I've been trying to restore a second hawk drive, and it's just kicking my butt. I am having a hard time with it. Everything I try, nothing seems to work. So I think I need to do a little more methodical testing, and the best way to do that is probably going to be to write a little assembly program. Now, writing assembly is a really interesting endeavor because it's a low-level programming language. Something like BASIC is a high-level language. So if you want to write, if A minus B equals 0, then go to whatever, 20 or whatever the next line number you want to go to is. That's pretty easy in BASIC, but if you want to do that in an assembly, it's a lot more involved because assembly is essentially telling the CPU exactly what to do step by step. So if I want to do a conditional statement like that, I have to first, load something into a register, load another operand into a different register, then perform the subtraction on them, and then branch if it's 0 or branch if it's not 0, depending on how I write the program, and then tell it where I want to branch to. So it's far more involved. Not only that, it has its own unique syntax. Processors like the 6502 or the Z80 are very well known, and the syntax for them is pretty easy to follow, but this doesn't have a Z80 or a 6502 in it. As a matter of fact, it's got a completely custom CPU card based around the AM2901 4-bit bit slice ALU. Now, granted, that ALU does have some opcodes of its own, but those opcodes are completely unrelated to the actual opcodes that we see as a user writing assembly. And that's because there's a lot more going on the CPU card. It has a 56-bit micro word that goes through and controls all of the individual logic. And so we actually have, I think, close to 256 opcodes that we can use with this CPU that allow us to do a lot of really tricky things. But I don't think we're going to need nearly that many. I think we can get by with just about 5 or 6 opcodes today. So I want to write an assembly program in Centurion assembly language that creates a loop and peeks and pokes the correct Hawk MMIO registers. So that way we can see what's going wrong where. And, well, because I'm a glutton for punishment, I'm actually going to write it on this machine. I'm going to use the working Centurion to build a program to diagnose the broken Centurion. So today is going to be something. I hope it's interesting, but let's get this one spun up and get started on it. All right, here goes nothing. I've got the Hawk spun up on the working machine here. I'm in the operating system. It says CRT0 ready, so we'll do a .sta to just get the status of the machine going on. And we're actually going to write the program using an application called Centurion Editor. Now, this is an application that was not one that came with Centurion. The text editing program that they used was called Compose, and it did not go well using it. So Rin wrote a new application for text editing. It's a line editor, and it is fantastic. And as a matter of fact, Rin, thank you so much for not only writing the editor, but all of your help. What we're doing today would not have been possible without all of the work that you've done figuring out the actual opcodes for this machine. But let's get started. We'll do s.ced, and we want to name the file zhwkt for Hawk test, put it on platter 1, and we want our output to be CRT0. So go ahead and hit enter. It's going to say it's not found. Do I want to create it? Yeah, let's go ahead and make that file. And here we are at the main prompt for CED. From here I have a couple of options of things that I can do. I can hit P to print out what we've typed so far. Now we haven't typed anything, so there's nothing to print out. I can hit D to delete certain line numbers, but I haven't typed anything, so there's nothing to delete. I can do C to change a specific line number, which is going to be extremely helpful if we make a mistake. I can do I to insert text before a specific line number, or I can do A to append text to the end. Now, because we haven't typed anything, doing A will just append text to line 1 because there's nothing before it. So that's what we're going to do. We're going to hit A and then new line, and it says period by itself to end. So let's go ahead and write our first line of assembly, and we'll start with PROG telling us that this is a program, and then we'll do begin, and then we'll do X single quote 0100 single quote, and then we'll go to the next line. And hooray, we just wrote our first line of assembly. This is just telling the assembler that this is a program, and it's going to start in memory location 0100. Now I chose that memory location because we know that that's a safe location to put programs. Anything below 0100 in hex is filled up with system stuff. Now, next we want to actually start our program, and we're going to give it a label right here at the top that we can come back to called top. So the first thing we want to do is we want to get the controller card set up correctly to select the correct drive and the correct platter. And we're going to use that, we're going to do that by storing a 1-byte value in a specific MMIO address. Now that 1-byte value is going to specify exactly which platter we want. And in Centurion land, you just count from top down. But I'm going to go with number 1. Number 0 would be, the removable platter. Number 1 will be the fixed. That's what we're going to work on. So we want to store 1 byte 01 into the correct MMIO register. But before we get to the MMIO register, we need to put that byte in a register in memory so that we can access it and use it later. And we're going to do that with the load A command. So we do LDA, and then I'm going to add a B on the end of here, and I'm going to put an equals, and then I'm going to space over to here and type X single quotes 01 single quotes. LDAB equals sounds like a strange way to write just load hexadecimal 01 into the A register. Well, all of the registers in the Centurion are 16-bit registers, and depending on the register, we can address the high byte or the low byte. And in this case, we're addressing the low byte by typing LDAB. And then the equals tells us that it is a literal value. So we are literally putting the value 01 in hexadecimal into the A register. So next we want to store that value into the correct MMIO address. So we're going to go all the way over to here, and we're going to hit STAB, and then we're going to do a slash, and then we're going to space right on over and hit X F140. So STAB means store the A register byte, and then that slash means that it is direct. So we're storing that byte directly into the address that I specified, which was hexadecimal F140, the MMIO address for the disk cards to set up and select the correct drive. So we're going to hit enter, and then we're going to come back over here, and we're going to load a new byte into the A register, so LDAB equals, and then we're going to load in 03. 03 is the command for RTZ. So if you put that value into the correct MMIO address, it should cause the drive to seek the heads all the way out to track 410, where it hits the forward into travel sensor, and then it counts back from 410 all the way to 0, and that makes sure that the heads are directly over track 0. So just like above, we'll do a STAB slash, and then we'll do an X single quotes F148 into single quotes, and that will get it to do the RTZ. Now that actually takes a certain amount of time. It takes something like 20 milliseconds or something like that. So we need to actually pause the program here to let the heads physically move out and physically move back. So we need to essentially run a delay. Now there is a delay opcode, DLY, but it's only 4.55 milliseconds. So we need to run that command several times. Now I could just do DLY, DLY, DLY in a row, and that would get it done, but It's annoying and it's kind of difficult, so we're going to set up a subroutine. But in order to run that subroutine, we kind of need to pass a variable to it. So we need to put a certain value in a register that subroutine can use to figure out how long it needs to loop and run that delay command. So we're going to do that with the transfer opcode. So that's XFR. So we'll space on over here and we'll do XFR and equals, and then we'll space right on over to here and we'll go X single quote, and we'll do, I don't know, 0, 100 single quote, and then we'll do comma Y. And so this is transferring the literal value 0, 100 into the Y register. Then we go to the next line and we just hit JSR/. Now this slash is really important because the jump subroutine can either be a relative address based off of where the current program counter is, or it can be an actual address. And this is what tells the assembler which one to use. And so by putting the slash there, it's just an actual address that the subroutine is going to be at. And so that's important because if it's a relative address based on the program counter, we only have a certain amount of distance we can go. We can go 128 bytes forward or 128 bytes backwards. If we're beyond that, we've got to change it over to this. So we'll do JSR/, and then the name of our subroutine we'll just call DELY, short for delay. Now the next thing that I want to do is I want to start a counter that counts out the number of cylinders. So that way when we get up to cylinder 410, which is the maximum number of cylinders, it resets the program back to 0 and it starts all over again. Now it's going to be a long, slow program, so I don't think I'll get that far, but it's nice to have that contingency in there. So I'm going to do a XFR equals, and then X single quote 3200 single quote comma Z. So we're going to store 3200 in hexadecimal into the Z register. That's our upper limit, the maximum number that we can count up to. Now I said that the Hawk drive only has 410 cylinders, which is 0, 190 in hex, so obviously these numbers don't match. But the address, or the MMIO address that stores this value, that cylinder address value, also stores the head selection bit and the 4 bits for the sector that we're picking. So on each track there are 16 sectors, and then there's an upper head and a lower head, so an upper track and a lower track. So the 5 bits that selects all of that comes first from least significant bit counting up. And then we have 9 bits for our cylinder address. So combining all of that up in the way that it's arranged here, the maximum that we can count up to is 3200. So we've stored that in the Z register and it's just going to live there. We're not going to modify it any later in the program. So we'll go ahead and go over to the next line here, and we're going to make sure that the X register is 0, because we're going to use the X register for counting up to that 3200. Now to make the X register 0, that's pretty easy. We just do a CLR and then go on over to X and then hit enter. That clears the X register to 0. Now next we're going to start our main loop. So I'll just call it loop here. And the first thing that we want to do is we want to store that cylinder address, which is in the X register. Now we just cleared it, but when we loop back up to here, we're going to loop to just after the clear. So every time we increment it, it'll just keep going up. And we want to store that in the correct MMIO address. So we're going to do a store X, and then we're going to do a slash on that one. And that MMIO address is F141. Now the value we're storing in there is 2 bytes, so it's going to put it in 141 and 142, but that sets up the disk cards to the correct cylinder, the correct head, and the correct sector. So next we want to tell it to seek to that location. We'll do a load B with the value 02. This is the command to seek. Now we just need to store it into F148, and again we're going to do that with a stab slash X F148. Now again, this takes time, so we're going to call up our delay subroutine one more time and delay for, I don't know, about hex 10, and that'll give the drive enough time to physically move to the next cylinder. It actually happens a lot faster than that. I'm kind of over delaying here, but that gives it time to stabilize. So that's the basis of our entire loop. Granted, I'm only in just the very beginning of it here, but there's a lot of repetition going on here. Essentially, we load a value into a register, and then we store that register into an MMIO address to get it to do different things. So we start by storing the cylinder address value into the appropriate MMIO address, and then we tell it to seek to that address, and then we want to set it up for writing. So we set up the write bit mask, which is at F143 to the correct value, and then we want to do an actual write. And so then we store 06 into F148, followed by 05 into F148, and then we give it another delay so that it gets that actual write finished, and now we want to read it back. And so to read it back, we do an F4800, that's the read command, and then we want to check the status. Did it read the data back successfully? If it didn't, we want to branch to error handling. If it did, we want to branch down to increment. And so that's where we are right now. Now, while typing that up, I made quite a few mistakes, and I caught them, so I went back and changed them using CED's fantastic interface, and that's why the screen looks a little bit different here. But now we're at a point where we're going to check to see if our read succeeded. And whenever you do a read, the status of that read is stored in MMIO address F144, and a clean read is going to be a 00. If there was any problems with that read, it's going to come back as something else. So we can just branch from here if it's not equal to 0. We do a B in Z, and we want to branch to ERR. This is our error handling. Now, if it was 0 and there was no error, it's not going to branch, and so it's just going to go to the next instruction. And so for that next instruction, we want to print to the screen that it was a successful read, and we're going to denote a successful read with a dot. So we're going to load a value into A again, so LDAB, and that value is going to be AE in hexadecimal. This is the ASCII value for a period. Now, if you look it up, that doesn't seem right. It's actually a 7-bit ASCII value, and the 8th bit is always set because Centurion is weird. So AE is Centurion's ASCII value for a period, and then that'll get sent to the terminal saying, hey, we had a successful read. In order to send it to the terminal, we're going to do another MMIO, but the multiplexer card lives at a different MMIO address. So we're going to do a STAB, and the MMIO address we're going for is an F201. And now our main loop is pretty much finished, so we want to increment our counter, and we're going to do that by just jumping to increment, JMP-INCR. So next, let's get into error handling, and we're going to name this label ERR for error. And the first error byte that can come back would be bit 1 of the high nibble is set, so that's going to be 10 in hexadecimal. And we'll load that into the B register because we want to use it as a comparison against what the actual error value is, which is stored in the A register. And we're going to do that by ANDing the two together, a bitwise AND. So we'll do AND B for ANDing 2 bytes together, and the 2 bytes are AL and BL. Now, Centurion works as source destination. So AL, which is the lower byte of the A register, is going to be ANDed with BL, which is the lower byte of the B register, and the result of that will be stored in BL. And so now if you AND 0001 with 0001, the answer is 0001. But if we have a different byte set because we got a different error message, for example, we got 0010, when you AND 0010 with 0001, you get back 0000. So we can do another branch based on that result to go to a different error handling for a different error message. So we'll do a branch if 0, and we will branch to ER2, so the next error handling location. However, if it doesn't come back as 0, that means that it was a match for a hexadecimal 10. We know that we have this specific error problem. And so in order to print that, again, we're going to load the appropriate ASCII value into a register, and that value is C6, which is the ASCII value for F, which stands for format error, and then we'll just store that into the MUX card and jump down to increment. And there are 4 total errors that we need to think about. There's the format error that we just did, there's a sector address error, so we'll print S for that one. There is a CRC check error, so we'll print C for that one. And finally, there's a timeout error, so we'll print T for that one. And that should take care of all of our error handling. Now it's time to increment. So we're gonna call it INCR for increment, that's what we've been jumping to up to now. And we're gonna transfer the counter, the X register, into the Y register. So we'll do an XFR X comma Y. And then we'll subtract our maximum that's in the Z register from the Y register and check to see if that equals 0. So we'll do a sub Z comma Y, followed by a branch if not 0 to INC2. Now this is interesting. So if we haven't reached 0, we're gonna branch to a different location. But if we have reached 0, we go to the next step. And that's because at this point in time, we're too far away for relative jumps, so we have to do some kind of inverse logic to make it work right. So the very next step, we'll tell it to jump to the top. And we'll do that with a JMP/top. Now, if it wasn't equal to 0, we branched to INC2. So that's the second half of our increment routine here. And so we're going to do a INR, and we're going to do that on the X register. So we're just incrementing the X register by 1. Then we're going to do a little bit of a delay to make sure that that actually takes correctly. And then we're going to do a jump to loop to jump back up to the top of our loop and start the process all over again. And then finally, the last thing that we need to punch in is our delay routine. So that was DELY, and the first step of that is just a delay. We're just going to do a DLY. That's 4.55 milliseconds right there that we're going to delay. And now we just need to count down. We set the Y register to how many times we wanted to delay, so all we need to do is decrement that Y register until it hits 0. So we'll do a DCR. We'll do that on the Y register. And then we'll do a branch if not 0 back up to DELY, creating a little loop here in and of itself. And when it is finally 0, we'll do a return subroutine. And that is our entire assembly program. We just finished writing it. Now we gotta see if it assembles. So we'll do a period by itself to end. We'll hit Q. And then we run the assembler just like we run the compiler. We'll do it p.asm, and we want to do it on HWKT because it automatically prepends the Z. That's on disk 1, and we want our output to be CRT0. Now, if I hit enter, it's going to ask me if I want to put it in the library. I'm going to say no. And error 0. That looks good. It assembled. Unbelievable. On the first try, kind of. I have a cheat sheet here that you've probably seen that I've been copying off of so that this video can only be maybe 30 minutes instead of 30 hours long. But it assembled. Now I can't execute it from the OS because it's not an OS executable collection of code. I actually have to type this into the memory monitor. And the reason that I ran it on this machine was so that I could see the assembly. And we did actually see the hexadecimal. It streamed by really fast while it was assembling. If I had changed the setting from CRT0 to PRT0, it would have printed that actual hexadecimal out on the printer, which is not working at the moment. It needs restoration. I'm going to get to it, I promise. It's next on the list after that guy goes up. But, well, I don't have a printer. So how am I going to get that hexadecimal? Well, it turns out the emulator has printer capability. So really, I just tested all of this in the emulator first, and that's the best way to experience the Centurion if you don't have the actual real metal in front of you. So if you are curious about playing with the emulator, there's a link to the Discord in the description below. join the Discord, shoot me a message, and I'll hook you up with the appropriate stuff to get into the emulator so that you can start writing assembly for yourself if you want to. But again, this assembly program is useless if it doesn't work. So I have the actual hexadecimal printed out. Let's punch it in on that machine over there and see if it does what it's supposed to do. All right, the Hawk is spun up and the heads have loaded. It's incredibly loud because there's no covers on it or anything. You can't get away from the sound of the jet engine in here. But there's a couple interesting statements about what I just said. The head's loaded, which means that there's heads in it. And if you saw the previous episode, that's special. We'll talk about that next time. But for now, I want to see if my test program works. I've typed it into the terminal here by hand, 1 byte at a time, and then I went through and double checked it, and I'm pretty sure it's correct. So all I have to do now is type G0100 to tell it to go to that address and start executing. It should do an RTZ right off the bat, and then we should start seeing something on the screen here. So let's do G0100, we'll hit enter. There went an RTZ, and we're getting something on the screen. I mean, it's not good. It says F, so that means that we've got format errors. I saw an S show up here, so that means that we've got a sector address error. That's showing up every so often. Oh boy, that's really interesting. But our program works. Our diag debug program actually works. And well, this is something that I can use to start debugging and figure out what's wrong with the Hawk drive. So we successfully wrote an assembly program on period correct hardware to diagnose period correct hardware. We only cheated very slightly in the center because I don't have a working printer on that machine. But if the printer worked, we could have done everything you saw today exactly as it was back in 1983, and I think that is awesome. I am super happy with this program, and I think it's going to be a big help. So I want to thank you guys so much for watching, and I hope to see you in the next episode.